All right, good afternoon, everyone. My name is Bill Renaud. I work with the Oak Ridge Leadership Computing Facility, and today we are continuing the presentation I began last Thursday on some Linux basics, somewhat of an angle towards HPC, although a lot of the fundamentals you would use on a regular Linux system as well. If you missed the first one, then this whole presentation will be available on the HPC Seminar Series website, so you can find the slides there to review that part of it. So let's see, move this out of my way here. So moving into part two, we will continue talking a little bit about working with files and directories and move into the notion of file permissions. So when you look at every file on the system, they have three basic permissions. Those are read, write, and execute. When we're talking about normal files like a word processing document or a text file or a program, readability basically means the person can look at the contents of the file. They could print it out or something along those lines. Write means they have the ability to update it, also the ability to delete it. An execute permission means they have the ability to run it as a program. For directories, it's a slightly different meaning for each of the permissions. Read permission means they can see what files are in the directory. Write means they can add and remove files from the directory. And execute means the ability to change into the directory. So that might be a little bit confusing. But as you experiment around on a system, you can create directories with different permissions and get a feel for what these different ones mean. You typically view the permissions with the -lowercase l option from the ls command. There's an example in the text box there. The permissions are that leftmost 10-character string. In this example, most of those characters are dashes. The first character indicates the type of file. If it's a regular file, which could be a program, a data file, text document, it will simply be a hyphen, a dash. If it's a directory, it will be a D, lowercase d. If it's a symbolic link, which we'll talk about in a few minutes, it'll be a lowercase l. The remaining 9 characters indicate permissions of that file for the 3 major entities that the system considers when granting access to a file. Those are the owner of the file, the Unix group to which the file belongs, and then everybody else on the system. The permission group is 3 characters, so there were 3 groups. There's a 3-character permission set per group, so 3 times 3 is 9, plus that special character if it's a file or directory that I just mentioned, and there's your 10-character string. So in order from left to right, those are for read permission, write permission, and execute permission. The way you tell if a permission is set is if the character R, W, or X happens to be present. That means the permission is granted. If the permission is not granted, there will simply be a hyphen. In the previous example, the user has read and write permission, the group has read permission, and other has no permission because of the dashes that are there. To change a file's permission, first thing that's you can help to remember the command is a permission is also called a file's mode. So to change permissions, you use the change mode command, what most people will pronounce as chmod, C-H-M-O-D. There are actually 2 ways to use this command, and we'll give some examples of both. One of them is symbolic, where you're using letters to stand for the different permissions. The other one is octal, where you're using a number, which is a little bit more difficult to pick up initially, but it is very, very powerful and is what a lot of people use as they become more familiar with Linux and Unix. So the symbolic way to run this command would be chmod, C-H-M-O-D, and then somehow specify the entity to which you're preferring. You see I have listed, that's going to be either U, G, or O for user, group, or other. Then you'll say what you're doing with the permissions, plus, minus, or equal. You are granting a particular permission, removing a particular permission, or with the equal sign setting a specific permission. And then that's actually a typo. The last thing on there is not the permission, it is the file name. So I'll need to update that before these get posted. The example at the bottom, the first one, we are granting the user read, write, and execute permission to myfile.dat. And the second line, we are taking away write and execute permission for other, that being everybody on the system except for the user and the group. And in the bottom example, that's a little bit more confusing way to call the command, but we are setting read, write, execute permission for the user, read and execute for the group, and read only for the other. That last example there is for a comparison to using the numeric way of setting permissions. So this is referred to as octal basically because each of the numbers will be between 0 and 7, so it's an octal numbering system. And this allows you to set different user group and other permissions all at once, kind of like that last example, but it's much more concise. To figure out the numbers, this sometimes confuses people. It can be a little hard to pick up until you get used to it. But basically you start with 0. That means no permissions at all. If you want somebody to have read permission, you add 4 to whatever number you're going to put there. If you want them to have write, you add 2 to it. And if you want them to have execute, you have 1. So let's say we want to set read, write, and execute for user, read and execute for group, and read only for other. That's exactly what we just did in the last example on the previous slide. So in this table, you'll see we want read, write, and execute for the user. So read is 4, execute is 2, write is 2, execute is 1. So 4 plus 2 plus 1 is 7. For the group, we want to give them read permission. Remember, that's 4. We don't give them write, and we give them execute permission. That's 1. So there's 4 plus 1 is 5. For other, we only want execute permission. So that's simply 1. 1 with nothing else to add to it is 1. So we would run chmod 751 myfile.dat. This one explains it a little bit better. You're using 4, 2, and 1 because you're essentially converting that permission group into a 3-bit number. So 2 to the 0th for the rightmost permission, that's execute. 2 to the 1st for the middle position, which is write, and 2 squared for the read position, which is the leftmost position. So that's where the 4, 2, and 1 come from. The table below gives some examples of looking at it symbolically, how it would appear in an LS listing on the system, how you might think of that as a binary format, and the actual calculation, adding up the numbers to calculate the value. The bottom example, I just called error number 2. That should be 4 plus 2 plus 0 for a value of 6. So a little more of understanding permissions, just to try to reiterate this one other way. Given the permission string that I have right there, dash RWX, R-X, dash, dash, dash. That file type is a hyphen, meaning that this is a normal file. The user has read, write, and execute permission. Group has read and execute, but not write. And other has no permissions. So again, for user, that's 4 plus 2 plus 1, which is 7. For group, it's 4 plus 1, which is 5. And for other, it is 0. So there are your 2 representations of that permission. It's 750 or the longer string that you see. Again, the symbolic method can be a little bit easier to grasp. You can set explicit permissions if you use the equal sign. Otherwise, if you're using plus or minus, it is not explicit. So you kind of need to know what the permissions are so that you know what to add or subtract based on whatever your operation is doing. For the octal method, it is a little bit more difficult to understand, but it always explicitly sets your permissions. And in terms of brevity, you can see it normally wins that game. In the example, both of those chmod commands at the bottom of the screen do exactly the same thing. One of them is far fewer characters than the other one. Remember, one of the nice things with Unix is we try to type as few characters as we can for things. Something else to understand: for any given user on a system, only one set of permissions on any particular file apply. So if you are the owner of the file, if when you do that ls-l listing, your username is the one that shows up, the user permissions apply. If you are not the owner but you're in the group permissions apply, and otherwise the other permissions apply. How that can be important: if you happen to set permissions of 077, that means everybody on the system except the person that owns the file has full access to it. Now, obviously, since they own it, they can change those permissions to something a little bit more useful, but you actually can create files that you cannot access. And we talked about the system administration account last time, the root user. Permissions don't matter to root. Root can read any of the files on the system. So they can read a mode 000 file. Sometimes you may see some extra characters in these permission settings, lowercase or uppercase, S or T. These are kind of what's called extended permissions, called set user ID, set group ID, and one that's called the sticky bit. They're a bit more advanced. We'll go through the slides quickly on these. The set user ID, if you see it on a directory, it's basically meaningless. Sometimes it has a meaning, but in most systems it doesn't. For executables, that means when somebody runs that program, the system thinks it is the owner of the file that is running it instead of the actual user that's running it. A good example of this is when you use commands to run things as the system administrator, even though you are not the system administrator. Those use the set user ID bit. So it's not the best word, but for lack of a better word, you trick the system into think of who's running the program. For set group ID, if it's on an executable, it's essentially the same as the set user ID flag. For directories, it's sometimes important and can be very useful. That means any files that are created in that directory will inherit the group of the directory. And any subdirectories will also inherit the set group ID bit. Normally, if you create a file, it uses the default group that's assigned to you as the group for the file. With set group ID, you can change that. That can be useful if you're in some type of work group where everybody has a common Linux or Unix group that they're sharing, and they have a collaborative directory. You can set this set group ID permission so that all the files have the same group, so hopefully everybody can access things. The sticky bit, also called the restricted deletion flag, is essentially meaningless for files, although it previously meant they hung around in some of the memory so that they could load much more quickly if you were going to run that program again. That was in the days when systems had far less memory than they do now, so it's really not that important, but it's actually where the bit gets its name. If you think about it, it's stuck around in memory, so the sticky bit. For directories, it means only the owner of a file can delete it regardless of the permissions on the directory or on the file. That can be important sometimes in a shared file system like /tmp/temp, where because of the nature of how things work, everybody needs to have full write access. It keeps you from being able to delete somebody else's files and keeps other people from being able to delete yours. These show up in the spot where you would expect to see the X for execute. So the set user ID will show up in where the user execute permission would be. Set group ID where the group execute permission would be, the sticky bit in place of the other execute permission. Files and directories need execute permission set for these special permissions to make sense. If you think of set user ID, it means when this is run as a program, the system assumes a particular thing about the user ID. Well, if you're going to run it as a program, you need to have the execute bit set. So you do need execute permission there. The system can help you notice if something is set incorrectly. If everything is good, if execute permission is set, then these permissions are represented by a lowercase letter that kind of blends in with everything else. If they're not set, you'll see an uppercase letter, which stands out a little bit more, lets you know there's something to correct. In changing these extended permissions, you can do those again either with the octal mode or the symbolic mode. With the octal mode using numbers, you'll use 4 numbers instead of 3. And the first number simply represents the special permissions, and I have what the 4, 2, and 1 stand for listed in the slide. Then the second, third, and fourth numbers in this 4-digit octal number simply represent your user group and other permissions. So again, here I have an example, and full disclosure, these permissions don't necessarily make that much sense, but they're great to use as an example. So in the first command, I've created a directory called mydir. I've done a chmod 7677 for that directory, and then I list it. So that's a 4-digit change mode command. So the first one refers to the set group ID, set user ID, and sticky bit. The other 3 refer to the user group and other permissions. And I'm basically enabling everything except group execute access, because that number is a 6 instead of a 7. So when I list the file, you see a big capital S in that spot telling me something is wrong. If I then use the symbolic mode to change group permission and grant execute, so G plus X, and then list it again, everything is lowercase, everything is what we would expect. Also related to permissions is this notion of what's called a UMask, which is a stumbling block for a lot of people, because people will tend to think of it as a default permission setting, and that's not what it is. It's actually quite opposite that. It is the permissions that you want to block out to prevent from getting set. So a UMask setting of 027 means you're blocking nothing for the user, because there's a 0. It means you're blocking write permission for the group, because that's a 2. And it means you're blocking everything for other, because 4 for read plus 2 for write plus 1 for execute equals 7. Settings for the UMask that are pretty common, you'll see 077, which basically means nobody other than the user will have any kind of permission set. 027 is a fairly common, fairly permissive setting. It lets you share things with other members of your group, but they won't be able to write over your files. And 007, pretty common as well. The UMask is not an absolute setting. What that means is it affects the initial permissions for a file. You can change those with chmod. So if you have the UMask of 077 that will block out everything for group and other, you can then go back in and grant those entities permission with the chmod command. A way to better visualize how this works, because again, it does tend to be a stumbling block for people. Think of the permissions in binary. If the UMask bit for any particular permission is a 1, that's kind of a wall. That's blocking the permission from going through. If it's a 0, it's a space that will let the permission pass through. If you are into binary logic and things like this, the way you figure out what the permissions are with the UMask, you take the default permission and negate the UMask and then do an AND operation. But not a lot of people think of things in that format. So to step through a bit of an animation to see how it works, there's our default permission for whatever file this may be. And the default permissions will be configured in some system settings, so you may not necessarily know what those are. And they will often change based on the type of file. Directories will have a different default permission than regular files. But in this example, we'll say our default permissions are 775. So that's represented in binary out to the right. Our UMask is 027, so we'll represent that in binary as well. But the way I mentioned you can think of it is the zeros are spaces and the ones are walls. So we'll change it to look a little bit like that, and it's a little bit easier to see what permissions are permitted to fall through and which ones get blocked out. So that gives us, then filling in the zeros for the permissions that could not come through, the resultant permissions of 750 for whatever file this may be. If you run the UMask command without giving it an argument, it tells you what your default setting is. If you give it an argument, you're actually setting it. So whenever I ran this test example, my default UMask was 027. I set it to 077 to be a little bit more restrictive. Run the command again to verify it, and we can see that it did, in fact, change it. And again, this is one that can be a little bit difficult to master. Create test directories on your system in your home directory and play around a little bit just to get the hang of things. In that first setting, I have my UMask set to all zeros, so not blocking any permissions. So then I created a file and a directory. I look at the permissions, and basically the file has read and write permission for everything, and the directory has read, write, and execute for everything. Then I set a little bit more restrictive UMask of 027. I created another file, created another directory, and you can see that that file does not have write permission for the group and does not have any permission for other. The directory is the same. It does not have write permission for group or any permission for other. So that can help you visualize UMask a little bit more. Moving on into the topic of links. These are simply ways to refer to files by different names. If you're familiar with Windows or Mac OS, Windows calls them shortcuts. Mac OS calls them aliases. They're essentially the same thing. We have two major types. They're called hard and symbolic. Symbolic links are sometimes called soft links. Mostly people are lazy and they just combine the word symbolic link into symlink because that's just a little bit easier to say. So to understand what links really do, it helps to have a little bit of technical knowledge of how the system actually stores things. You can think of a file stored on a disk as simply a bunch of bytes, a bunch of zeros and ones at some particular address. The name of that file, the thing that we interact with when using the system, is a pointer to that address. That address is something that's called an inode. Think about an index node. And a hard link, one of our two types of links, the hard link, simply creates an additional pointer to an address. A symbolic link creates a pointer to a file name, so a pointer to the address. Okay, graphic can help explain that a little bit. So we have file name A and file name B. Those are both hard links which reference some address. The inode in this example would be 12345. And then this box at right, which represents our file, also has some additional data: the user ID, the group ID, what time it was created, several other pieces of information. And then it has all of the data, just represented there by the zeros and ones. The bottom left, symlink A, represents a symbolic link to file name B. So symlink A kind of points to file name B. File name B is what actually points to the file on disk. And another thing to keep in mind with hard links, file name A and file name B, which one of those is the original file name and which one of them is the link? They're both file names for that file. When you create a hard link, you can't tell which one was the original file name and which one was the additional one because they're both identical. They're doing the same thing. They're a name pointing to the address. Whereas with a symbolic link and a pointing to a file name, you know that the file name was the original thing and the symbolic link points to it because, again, it is a pointer to a file name. We create links with the ln command, another good short command. The -s you will see is in brackets, so that means it's optional. If it is there, it says create a symbolic link. If it is not there, it says create a hard link. One good thing to keep in mind with the file name and the link name, don't put them in the reverse order. Most operating systems nowadays will not let you do this. They'll block that operation. There's probably a few out there, and certainly with older operating systems, they'll happily do whatever you ask for it to do, even if it means kind of destroying your file. So you don't want to put those in the wrong order. The way I always remember it is which order to put the file names in there is for ln-s, x, and y. That means to create a link to x named y. So the original file is what comes first. The link name is what comes second. There are some differences between hard links and soft links. You may wonder why we have both of them. Hard links have to exist within a single file system. I would say a single disk. That's not necessarily true because you can, with RAID and technologies like that, put multiple disks together that make it look like one very large storage area. But with your individual file systems, hard links have to be contained completely in that space. The reason for that is these index nodes are unique to a file system. If we have some bunch of storage on in one place and a large amount of storage in another place, both of those will have addresses, they're inodes, that say start at 0 and go up to whatever the maximum number is. So the inode for any particular file only has meaning within a particular file system. So since a hard link is simply another pointer to that inode, it has to be on the file system where that data resides. A hard link also cannot point to a directory. It actually has to point to a file, whereas symbolic links can point to directories. Symbolic links can also span different file systems. Why is that? Because they're simply pointing to the file name, which is unique across the computer, not unique within the file system. So they can point to the file names, they can span different file systems. What about permissions on links? For hard links, again, they just look just like regular files because that's what they are. Symbolic links have some unique looking permissions. It may scare you the first time you look at one because it looks like it has full permission for everybody on the system to go and be able and read and write whatever file you're linking to. But that's not the case. The permissions on a symbolic link are really ignored. What matters is the permission on the target file that link references. So when you see that L, RWX, 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 you don't need to worry about that because that's just the way symbolic links work. In my examples here, you'll see I've added a new option to the ls command, the lowercase I, so ls-il. The I means show me the inode number. That's the number that's out to the left. What is that? 37,930,848. So for some file, a file that I created. Then I do ln a file a link. So create a hard link to a file named a link. Now I do that ls command again, and the files are indistinguishable. The only thing that differs on those two lines is the name that's all the way out to the right, because they are both hard links to the same data on disk. Then I create a symbolic link. Let's create a symbolic link to a file named alink2. In the bottom example, you see the files that are created. Again, we have different permissions for the symbolic link. In this case, for whatever reason, it doesn't have the right permission there. Again, we ignore those because it's the link of the permissions of the target that matter. All the way out to the right, you see alink2 and then hyphen greater than, that's just making an arrow, and then a file. So that's telling you alink2 is pointing to a file. So both the existence of that little pointer and also the L as the leftmost character in the permissions are telling you that this is a symbolic link. Again, once the hard link is created, you can't tell the difference between it and the original file because there is no difference. You can delete either of those and the data remains in place. A file isn't truly deleted from the system until all hard links to that file are removed. Technically, at that point, the system is just told you can reuse this disk space. It's not actually cleared out, but recovery is very, very difficult at that point. So if you think about it, the remove command removes a hard link, not a file. From the user perspective, they're essentially the same thing. But you may be curious, that's why in some programming languages, the delete operation is not called delete, it's called unlink. That's representing what it's really doing. If you delete the target for a symbolic link, that's a little bit different than deleting one of multiple hard links to a file. Remember, the symbolic link is pointing to the file name. So if you delete that file name, that creates what's called a hanging symbolic link. It's pointing to nothing. Different operating systems will have different ways of notifying you that that's symbolic link is a hanging symbolic link. One of the best ways you figure it out is you try to use it and the system doesn't know what to do because there's nothing there. Moving into a little bit different topic, combining commands. Sometimes on a system, we want the output of one command to be used as the input to another. Now, in the previous seminar, we talked about doing file redirection with redirecting the output and redirecting the input. So you could do that to capture the output from one file and then pass it to another one, but that can get really confusing and that can be a little bit inefficient. So if you want to do things basically on the fly, you can use the pipe operator. The vertical bar, it's on the same key as the backslash on just about every system I've ever used. And the reason it's called the pipe operator, if you think about it, it's a pipe taking the output from one command and sending it into another. So kind of a plumbing reference there of the pipe carrying things from one place to another. Let's say, for example, you want to list a huge directory. Maybe there are several hundred files in this directory. If you do a normal ls-l and press enter, all of those files will fly past your screen in a couple of seconds at most. So there's really no way for you as an end user to see all of those files and do anything useful out of it. So if we think, if only there was some command that would let us display a screen full of data at a time. Well, if you remember, one of the basic commands from the last seminar was the more command that will do this, show you data a page at a time. So what we want to do is take the output from the ls-l command and send it to the more command so that we see it just one screen full at a time. So we can use ls-l, then the pipe symbol, and then the more command. So that will send the output from ls-l into the more command, show you the data a screen full at a time. Another very handy command, kind of called it there the Uber command, is find. This is personal opinion, of course, but this is one of the most useful and one of the most, if not the most powerful command that most users have at their disposal. As its name implies, its basic purpose is to search for files. But the criteria that it can use is very, very flexible. Criteria are very flexible. It can be timestamps, users, many other things can be taken into consideration for this search. And it also has the ability to take and run commands on the files that it finds. So this can provide a little bit safer alternative than using a recursive operation. Remember, one of the things I mentioned of being careful about was recursion, because you can sometimes do things you didn't intend to do. So we have some directory, or in this example, we have a couple of directories, /data/dir1 and /data/dir2. Let's say they're owned by some user, or these contain many different files that may be owned by many, many different users. We want to take all of the ones that are owned by user Phil and give them to the user named Sue. Maybe Phil changed work groups and Sue replaced him, so we need to change those files over. It can be very tedious to try to find them one by one. We don't want to use a recursive operation because people other than Phil and Sue have files in this directory and we don't want to affect those. So we can use the file command, or the find command. We tell it where to look, /data/directory1 and directory2, and find files that are owned by Phil. That's where the -user comes in. So find files whose user is Phil, and then this -exec option says run this command on whatever you find. So -exec chown Sue, and then we have some kind of interesting syntax. This is just the way the find command works. So this says find files in these directories that are owned by Phil and change ownership of those to Sue. So that's how we can run that particular operation in those directories. Sometimes we may need to search within files, find a particular text string that occurs in a file. The grep command stands for, at least at one point, stood for Global Regular Expression Print, is why it's called grep, kind of a really confusing acronym there. But as its name implies, this uses regular expressions. Remember, I mentioned the other day, regular expressions are a topic unto themselves. I think there's a kind of a handbook on them that's several hundred, 800 to 1,000 pages, so a very involved topic. You may also see some advanced versions, egrep, I think fgrep is the other one, I can't remember offhand. Again, those are very involved topics, so if you care to investigate those a little bit more, feel free to do so. Moving on into a little bit different topic, process management, something that we often do on the systems. Everything running on a Linux system or a Unix system is a process. Remember, the system likes to deal with numbers, so it views everything as a process ID. And we can interact with a process via its process ID. Maybe we can make it a higher or lower priority. Maybe we want to stop the process, also called killing the process. There's two major types that we deal with, a foreground process. This is what most commands are. You run the command, you press enter, and you have to wait until it finishes before you get your prompt back to run other commands. So they're higher priority because they block you from doing other things until they complete. There are also background processes. These run at a lower priority. They run as they can between higher priority tasks that are executing, and they permit us to run other commands while the background process is still running. We may know we want to copy a very large file that's going to take 10 or 15 minutes. We can background that copy command so that we can keep working while it's going. To make a command backgrounded, we simply put the ampersand at the end of the line when we're starting it. So in the example there, we run some task and background it. If a task is already running and you start to think, oh, I need to do something else, this is taking longer than I expected it to, you can press Control-Z. That will stop the task from running, give you your prompt back, and then you can type BG, BG for background, and press enter. That says move that thing that you just stopped into the background. If we had a background process and we want to move it back into the foreground, we can just type FG, and that will move the command back to the foreground. Again, FG for foreground. You can only foreground one process at a time. Remember, those are blocking, so if you need to know, or if you have multiple backgrounded processes, you need to tell the system which one you want to bring to the foreground. There's a command called jobs that will show you what processes are backgrounded so that you can know what to tell the system to bring into the foreground. All processes are started by other processes. The process that starts another process is called the parent process. Processes that it starts are called child processes, so that kind of makes sense with the naming of those. You can view these with the PS command, PS for process. These show the process ID called the PID and the parent process ID called the PPID or PPID. If you trace things all the way back, which is possible to do, you'll see everything on the system is started from a process that's named init. That's the process that initializes everything on the system. So some common options to PS on most Linux and Unix systems. The -F option will show a fuller listing. It shows some extended details. The -E option will show everyone's processes on the system. Normally, if you just run PS, it will only show you your processes. The -U option will show you process belonging to a given user. So to show all processes that are running on the system, you would run PS-EF. If you only wanted to show processes belonging to user John, let's say you want to use the full output version of this, so you have the F there, and then U is used to show username John as the only one that you want to display. So you have that command to show all the full detail for processes by user John. PS is like several Unix commands. If you're using several different options, sometimes it lets you put those together. So in these examples where I have everything together after the one dash, you could just as easily run PS-E space -F or PS-F space -U space John. Those would be equivalent. It allows us to use this shorthand sometimes just to save keystrokes. We can also communicate with processes, and they can communicate with each other via what are called signals. Some of these happen automatically. If we're running a program that does some type of illegal math operation, that will cause a floating point exception, which actually creates a signal. Some of these are done explicitly by users via the kill command, which is actually a misnamed command because kill is a particular signal, but the kill command can send many different signals to a process. The syntax that we use for it is kill space the signal space the process ID. That's where the PS option becomes handy to find out what the process ID for a particular task is. There are some special cases for process IDs of less than 0, things like killing all processes that you currently have running or all processes in a particular group. You can look on the info or the manual page to get a little bit detailed information on that. Your scripts can also interact with processes. This is what's called trapping, and it lets you do things like perform an orderly shutdown or have the program perform a certain action when it receives a certain signal. Not all signals can be trapped. So there are references online that can tell you which ones can and cannot be trapped. And you can list available signals on a system with the -L option for kill. So kill -L for list. Important to realize that example, the command that I have there, that is a lowercase l and not an uppercase 1. So there's a good example on one of the systems that I work on, kill -L, and there are 64 of them on that particular system, so quite a few. Some of them I know what they mean, some of them I've never encountered. They're particular to this system. That's because only a certain number are actually predefined. So some of them that are pretty commonly used, there's a signal called hang-up or SIG HUP. It tells a process that the user terminal went away. Remember, on most of these systems, you remotely connect to the system, and this name of this signal goes back to the early days of computing when you were connecting via a phone line, and the phone line got hung up. So that's where the hang-up comes from. SIG int, or interrupt, that tells a process that the user typed Control-C. One of the ways you stop a command from running, if you didn't mean to type it, is you can type Control-C, and that will interrupt that process. There's another one called SIG quit, which is similar to an interrupt, but it dumps what's called a core file. That's basically a representation of what memory was when the process ended that you can use for debugging. SIG abort is normally when the program detects some kind of error and bails out. It stops itself from running, and that's reported through signal number 6. Then the last two are similar to each other, kill and terminate, SIG kill and SIG term. Going out of order from this table, the SIG term is essentially asking the process, will you please stop running? SIG kill, signal 9, is cutting the process off at its knees. It is go away, stop running, no matter what. And that is one of the signals that cannot be trapped. If your program receives a signal 9, it must end. There's some others that I have listed that you can encounter: an illegal instruction, floating point error, segmentation fault, which is normally an illegal memory access in a program, array out of bounds or something like that. There's also some user-defined signals, which convey no particular meaning on the system. They mean whatever you intend them to mean and tell your program to react to. For the number of those signals, you see I have a lot of question marks. That's because they vary from system to system. They are not in the different standards documents explicitly said SIG illegal instruction is a particular number. So again, SIG kill, SIG turn, SIG end, tell a job to end, but in varying ways. And we discussed Control C and Control Z. They're just redefined there a little bit. File compression is just some file maintenance utilities. Sometimes you want to compress a file to save disk space. There's several utilities that we have: GNU Zip, Zcat, which is essentially the same thing as GNU Zip, but instead of compressing a nice file, it sends everything to the standard output. Why would you want to see all of this file compression coming to standard output? Because it's going to be nonsense on your terminal. Well, remember, we can create commands where we pipe one command into another. Maybe you want to send that compressed data into some other command. That's where that would be useful. There's another one, bzip and bzip2 and bunzip2, simply a different compression tool. If you're familiar with zip files on an OS like Windows, the names of these are a little misleading. Because the zip utility on Windows does two things. It combines files and compresses them. On Unix and Linux, remember, commands are single purpose. So the zip command is what compresses a file. If we want to archive files and combine them, there's another command called tar. This one is another one whose name is more historical than anything else. It stands for tape archiver, even though most systems don't use tape anymore, but it still works very well. And it combines files into a single archive, or it extracts files from an archive. Some versions of it have an option to go ahead and do compression. Otherwise, you can run tar and then gzip or bzip the result. File ownership, we talked about files having owners and groups. Well, sometimes you might want to change the owner or the group of a file. To change the group, you use the chgrp, chgroup command. To change the owner of a file, there's the chown command, change owner. However, most users will never use this command because you can't. Only the system administrator can use the change ownership command. That's basically so that you can't. On some systems, you will have a storage quota that prevents you from using up all of the disk. And if an individual user could use the change ownership command, you could take all of the files that you own and change them to somebody else's ownership so that you're pushing them over quota instead of yourself. So you can't do that. We also often do string processing on these systems, both system administration and for day-to-day use by end users, because a lot of things get stored in configuration files. Sometimes we need to manipulate this data or just parts of this data. So there are several utilities that can do this. And this is also a good example of combining some basic commands. So there are different commands for searching text files. We talked about grep for searching it. Also for processing text files, there is a sed, which is a stream editor. There's another one called awk, which seems like a really odd name, but it's the first letters of each of the three creators' last names. The Perl command/programming languages, many, many more. Each of those could be a class by itself. They all involve regular expressions. There's lots of references available for that. But let's assume we have a file that is full of address information for some registration list, I don't know. And it contains lines that have first name, last name, street address, city, state, zip code, phone number. And we've been asked to provide this, the different zip codes from this file for whatever reason. How many different zip codes are we mailing this information to? One of the commands that we will use is the cut command. That, if you think about it, takes a lot of data and cuts it into smaller pieces. So we give it a delimiter with the -D option, and that breaks it into the different fields. So in our example, the zip code was the 6th field, and these were all delimited with colons. There were colons between the fields. So we will use the cat command to show that file, and we pipe that to the cut command and tell it the delimiter is colon and only tell me field 6. So that will list one line for each line in the file, and it will just show you the zip code. But yeah, that's nice, but why can't we put them in order? Okay, well, the sort command can put those numbers in order for you. This can do a numeric sort if you give it the -N option, or it can do an alphabetic sort, which is the default. You can give it specific delimiters and keys. Let's say you want to search on the 3rd field instead of the leftmost item. That's a little bit beyond the scope of this example. So we want to sort numerically. So now we add pipe to sort -N to that command. So we're sorting numerically. Well, that's great. We've got everything in numerical order. It's sorted, but we only need to know the zip codes we're using. We don't need to know that we're using a particular zip code 15 different times. So can I get rid of the duplicates? Well, there's another command, unique, UNIQ. This removes duplicate lines. Now, the important thing about it, it removes adjacent lines that are duplicate. That's why we had to sort it first, so that all of the common lines are put together. So again, given our data file, we cat the addresses file, cut it so that we're just looking at the zip codes, then sort those numerically, and then ask to do that through the unique operator, so we only see one line for each zip code that we're using. So that kind of goes back to remember Linux having single purpose commands and that they can be combined to form a more complex command. So that example took 4 basic commands to create a much more complex one. The 4 basic ones are listed there. The more complex command was show me the sorted zip codes from this particular file. So that's how we combine those commands together to more powerful ones. Just touching on a couple of more advanced topics as we wind this up. On desktop systems, if you're running Linux on the laptop or as a desktop machine, you'll use a lot of graphical tools, window managers, file managers, web browsers, and email. The system that runs this is called the X window system. Sometimes you'll call it X11. If you're setting up a system now using X, it's no problem at all. Everything basically gets auto-detected. If you were doing it 10 years ago, that might take an afternoon to get everything configured correctly. Much nicer now. You also sometimes will use graphical interfaces on remote systems where you connect, to a lesser extent, but for things like debuggers and profiling tools. And the problem with this is X11 traffic over a network is pretty easy to configure, but it is very, very slow, very unresponsive. So we have some tools to mitigate this. One of them is called FreeNX. There's a URL to one implementation of it. There's VNC, Virtual Network Computer. These require some setup both on the server and your client system, so you might need to work with the administrators to have those set up. But they do some compression and they do some other things that mitigate the amount of traffic that's actually being sent over the network, so it makes the response much, much faster, much easier to use. In particular, if you're using supercomputers, you will encounter what's called a batch system, a batch scheduler. This is because it's a shared resource and lots of different people are accessing this system to run their jobs. There's lots of different batch queue systems that you might encounter, Moab and Torque, which is what I'm familiar with on the system that I encounter most of the time. The portable batch system, PBS, load leveler, load sharing facility, or LSF. They all essentially do the same thing. They give you a way to submit and manage jobs. They give the system operators a way to prioritize those jobs and make efficient use of the resources. But the commands for each system and the nuances of using them will differ slightly from one to the other. But it's one of those things like programming languages where once you've used one, you essentially know the basics and just need to know the minor things to change to use another one. Using batch systems, you use what's called a batch script. This is a shell script. We mentioned those last time. That's essentially a list of commands telling the system you need to run this command, then this one, then this one, whatever's necessary to run your program and run your simulation. They also will contain some metadata about the job, how long it's going to run, how many processors it uses, maybe what project to charge, the runtime for this job. All of those will be, again, particular to the different system. You submit this to the system, and the software on the machine takes care of scheduling that. It is important to give good estimates of your processor needs and your how long your job will run, because that makes the scheduler a little bit more efficient. Going into this in much more detail gets very, very system specific. Most centers where I've either worked or used systems have some pretty good user guides on their websites that can give you those low-level details for each system. Couple of resources that you can use just in general for information on some of what I've talked about, and might go into some additional information. The first URL I got, I referenced at the very beginning, is finding some examples there. That's a good Unix introductory course. You might want to go through that in your leisure time. Also, I'm typically a fan of the O'Reilly Media books for different programming languages, and they have one that's Linux in a nutshell. I don't know if they have a new version coming soon. The current one is several years old, so newer systems may already be outdating it a little bit, but hopefully they'll have a new release of that. And that's a really good reference to have on your desktop. I've got a couple of the nutshell books that, even though I've been using particular OSs and programming languages for 10 or 15 years, I still use those reference guides. And then some more advanced topics. I have listed there different editors that you might use. If you remember in the first session, I discussed that shells are very much a matter of personal preference, and people are very quick and very vocally defend their shell of choice. Same thing with their editors, in particular between VI and Emacs. Most people will use one and will not even consider the other one, just the way a lot of users are. Some special files that might come in handy when you're using the system. I use dev-null in an example. There's also one that gives you some random data. There's one that gives you a string of constant zeros. Email and web tools, some utilities to schedule tasks. One is called apt, one is called cron. Regular expressions, and going more into scripting and system administration. Package managers, which is how we install software on the system. Again, I talked about some more advanced batch queuing system setup. Aside from that, if there are, I'll just open if anybody has any other questions. And also, if you want to, please feel free to provide any feedback, either to me, I have my email address there, or also to the Nix team of what was good in this presentation, what needed help. If you prefer seeing a lot of commands or kind of some practical examples, I tried to do a little bit of both in there. And in the first seminar, I did a lot about the background information. I'm not sure if that was too little, too much, or interesting or not. So I'd be interested to hear any comments that you might have on any of that. And with that, if there are not any questions on the chat, then I will thank you very much for your time, and hope you did find this set of presentations useful.